All right, so the format for this video is we're going to cover factorial, and we're going to do it recursively. We're going to cover the recurrence relation first, implement it in C code, and then we're going to implement it in assembly. Just a couple of notes here about factorial. Factorial, as far as like its recursive solution, purely academic, what you'll see is that every call to the function allocates a stack frame, which itself is a very costly process. It turns out that for like linear algorithms, if it's like O of n, and then the recursive solution is still O of n, you should not implement it recursively as a function. You should just implement it as a for loop. So please remember that for like technical interviews and stuff, unless the dude is explicitly asking you to implement it as a functionality, providing the functional recursive version of an algorithm when an iterative one with a for loop would cost you some points there, okay? All right, so recurrence relation for a factorial, all right? If I write this, factorial of 0, what is the result for that? 1, right? Okay. Factorial of 1 is what? 1. All right. Factorial of 2. So this is, if you've never seen this before, factorial of like 2 bang, 3 bang, it's sort of like this, all right? I could probably come up with some weird math notation to describe this, but hopefully that's clear that when you do the factorial, it's sort of like you multiply it by that number and then minus 1 until you hit 1. Technically, there are 2 base cases because you could actually end up, 0 is a potential number for the domain there. F of n is equal to n times a recursive call to this definition to insert n, but here you can see it's actually n minus 1, okay? So let me just write this out here. So it's equal to 4 times 3 bang, right? At least that's how I have it written down. You write the argument down and you multiply it times a recursive call to itself where you decrement the argument, all right? This here is 3 times 2 bang, right? And then this thing is a recursive call to itself for 2, which is 2 times 1 bang. However, that is one of our base cases, which should return 1. All right? So that is a pretty good example of recursion, where it ends up calling itself, and once you hit the base case, it just sort of returns, the base case being 1 bang. Okay, so how do you code this thing up? So one way to do it, int fact integer n. For this to work, there has to be a base case. So that would be if some condition return 1, otherwise return n times fact of n minus 1. All right? Okay. What condition should that be? Can we aggregate that into a single conditional based on what we see? I guess we could like just say that the domain is like positive integers including 0, and then just hope that they never actually give us a negative number. I don't know. We'll just run with that, okay? So basically we'll say if n is, let's say, less than or equal to 0, then, or less than or equal to 1, sorry. If it's less than or equal to 1, then just return 1. And again, we're assuming here that the domain stops at 0 and the user wouldn't troll us by giving us a negative number, okay? And if you're wondering why it works, this is basically a good hand trace of what would happen. It would, you're calling fact 4, where 4 is the input here. This statement is false, so it falls into the else block, and it attempts to return 4 times a function call to itself, where it decrements that n you're giving it, that ends up being a recursive call, and you repeat that until finally you end up in a situation where you end up calling fact of 1, in which case this statement would be true and it would return 1, and then it would return up the chain, inserting, like, accumulating that multiplication of whatever with the previous return value until you finally get up here and you get the original value, okay? Why would you ever use factorial? You know, I don't know. I don't think I've ever gone over an algorithm that actually involves the factorial as a functionality in the algorithm, all right? It's just a very common example in computer science because it's just like a great example for recursion. Why you care about it for this class is the only way to make a recursive function work at the assembly level is to use a stack frame, because when you call a function, you are actually re-entering the function at the same point, and every instance of that call implements its own stack frame. So here, what will happen is a stack frame will be created for 4, basically. So 4 would allocate its stack frame, then 3 would allocate its stack frame, and then 2 would allocate its stack frame, and then 1 would allocate its stack frame. And each one of these stack frames, it would save the return address at the bottom until finally you keep popping it until you get to the outermost call and it having the return address back to main. On top of that, having shadowed that input argument n in each one of these frames would allow it to remember the specific version of n equal to 4, n equal to 3, 2, 1, relative to that local recursive call, okay? All right, so let's go ahead and implement this thing in assembly. It's called fact, so I guess we'll start there. We'll just call it fact, all right? So if you're following the previous videos or lecture, the common things you're gonna do when your function gets control, you're gonna allocate space on the stack. For your frame, you're going to save the return address, the frame pointer, as well as do a shadow copy on the arguments. All right? Speaking of the arguments, it looks like this thing is going to be in W0, right? Because it is an integer argument and it has to be W and not X, because standard integers are only 32 bits. And, you know, it looks like this is pretty standard here. Everything's going to be 32 bits. So basically, incoming in W0 is going to be n, and the outgoing return, whatever it might be, the base case or the recursive call, are also going to be in W0. All right? So to start off our function, we will move the stack pointer by subtracting. Stack pointer. I don't know how much space I'm going to need. I'm going to allocate 64 just because, okay? So we will store x30, x29, as well as a shadow copy operation on W0, all onto the stack. We'll put the return address at the bottom of the stack. Remember, because this is x, it's 8 bytes. So the next free space on the stack would be SP plus 8, all right? This thing is also 8 bytes. So the next free space on the stack would be SP16. All right, so there we go. That is basically setting up our stack frame, placing the return address at the bottom, the frame pointer just above that, and then shadow copying our input argument onto the space just above all of that, okay? All right, so what do we have to do here? So the base case here says if n is less than or equal to 1 to return 0, all right? So at this point, W0 should still contain our input value of n, so I can compare it directly, do CMP W0 to 1, and what I'm going to want to do here is leave the else in the fall through slot, all right? Just because I'm lazy and I want to handle that return 1 at some other point. I want to handle the recursive solution first, okay? So branch if less than or equal to, we will just call this ret1, and then I'm going to code that later, okay? So that means that we're kind of done with this, and that means that the fall through slot is now the else, basically. We now need to return the concept of n times fact of n minus 1, all right? According to our order of precedence, which is the way in which we resolve complex expressions, a function call is the first thing you must do, followed by the multiplication on multiplication with n, and then actually there's no assignment here, so that would be it. It's seemingly a two-step process, all right? So let's handle that. So that would be, I guess the first thing we have to do is set up a call to fact. If we're going to call fact, fact will expect the argument n in the register W1. So currently W1 holds n, and it still does. I haven't modified Wn. So what I'm going to do is to just subtract a value of 1 from here. So what happens is, what happens here is that, if I said W1, I meant W0. The W0 is assigned n minus 1, okay? Now, there might be some panic on your end because here, at this point, we have clobbered what we believe to be n in the scope of our current function call, but I want to point out that on entry to the function, we had saved the value of n onto the stack. So even though we had modified this value to be n minus 1, if we ever need to refresh the original value of n, it should be located on the stack at SP16. Okay? So we set up our call to fact, and then we recursively call fact. So that's just BL fact, all right? How do we know it's going to work? Well, we're coding it. It's going to work, okay? So what happened is it would literally jump up, basically, and repeat all of this. So after this instruction, what I'm going to ask you to do is assume that the function had worked, okay? If the call to fact worked, where should the result be placed? N is in W0, right? So that means that here, W0 should contain the result of fact of n minus 1, all right? Why? Because we're going to code it like that, okay? All right, so what does that mean? So basically, we're done with this thing now. We made a call to fact and are assuming it's going to work. We now need to multiply it by n, okay? What I'd like to do is do the wrong thing, and then we'll discuss why it's wrong. Mo W0, W0, W0. Okay, this is obviously wrong, all right, because W0 had been changed by the previous function, and you might be using W0 again in the hope that it's still n, but we modified it here, and fact was called, and you should never assume that the value of an unsaved register will be the same on any function call, even if you are coding it, okay? So, yikes, that's not going to work. Okay, so if I need n, though, what should I do? I think we saved it on the stack, right? We saved it at this position, SP16. So basically, when we return from the function call, what we can do is refresh the value of n. Let's put it in a different register, not W0, because W0 should contain the result of the function call. And we will load SP16 off of the stack. So now W0 here, or I'm sorry, W1 should now contain the value of n. So if I want to implement that expression on the return, I need to multiply W0 and W1 together. Okay? So we'll do that. Mo W0, W0, W1, and then what I'm going to do here is just leave it, actually, because I strategically chose W0 as the result, where I want to place the result of multiplying these two numbers together, because the concept of the return is that you place the result in W0. So by doing this, I don't need to move the result anywhere anymore, because the result should be in W0. So if we're all good, basically, that's literally the end of that recursive call. You can now return, all right? This is not a leaf function, because it ends up calling factorial. So you have to restore you end up having to restore the return address x30. There's at least 3 commands here. And what I'm going to do, this will make sense like later. I'm going to label this point as done, basically, because I still have to implement the return 1 code, all right? So we'll call this done here. I'm going to load, all right, the return address. I place the return address in stack pointer. I generally always place the return address at the bottom of the stack frame. Then we're going to pop the stack by adding the exact number of bytes that we allocated. I noticed that it's 64 up there, so I'm going to put 64 again, and then we're going to return. So that concludes the recursive part of the code. We still have to add this base case code. So I called that ret1, so that would be somewhere else in the code. It would say ret1, and we need to return 1. So I will just move a value of 1 into W0 and then branch to done, okay? So basically, let's just double check that logic to make sure that makes sense, basically. So we already handled the recursive call. On the base case call, if n is less than or equal to 1, that's this, jump to the code that should return 1. And again, just a reminder, in order to do that, you have to place 1 into W0, which I've done here. It jumps to done, which is code used by both of these branches to return to the caller, whether it was a recursive call to fact or to main, basically.
All right, so in part 2 of the video, what we're going to do is implement this thing on our server. So this server is a AWS EC2 instance, and we're using GCC to test this function. So in order to test our function, it's only a functionality. We'll actually have to have a main that makes sure it's running properly. In this instance, what I'm going to do is have GCC help us out and to implement some things that aren't really relevant to the video. So for example, how to call printf, how to implement a main. So what we're going to do is we're going to start with a main.c. All right. We're going to include stdio, which has our printf, and we're going to insert a template for a factorial function. And this factorial function will basically do nothing. All right. Return 0. The point here is that we'll have GCC convert this thing to assembly and insert our assembly code to replace that return 0. All right. Then we'll have our main function. It doesn't have any arguments. We'll need a return 0 because remember, 0 is the code for exiting the process without any errors. And then we will call a printf here with %d. And so this is a token for an integer with a new line, and the argument will be a call to fact of 5. All right. Okay. Let's compile this thing and see what GCC has done for us. All right. So the command you're looking for is GCC. We'll display all warnings, have no optimizations. That big capital S is the flag to generate assembly code from C code. We want the output to be main.s, and the C code we want to compile is main.c. All right, cool. Let's take a look at what main.s is doing. So one of the most important aspects of being a programmer is to look at some code that was given to you and to identify the relevant portion. Here we have main. Main was set up and should work properly. All right, it was pretty simple. It was the factorial code that we need to modify. So it looks like this here is the beginning of the factorial code. Let's insert a comment here. This is the beginning of factorial. Let's try to find the end here. I would say that this right here, this part, is the end of our fact code, like so, because this is the start of some read-only data. All right. So, how do we modify this? So if you remember, this looks a lot like what we were doing, but we actually allocated 64 bytes of stack. It looks like it shadowed W0 onto position 12. Actually, the way we were doing it, we shadowed it onto position 16, and we're going to store the return address at SP, and we're going to store the frame pointer at SP8, and then let's see here. So our code, okay, so I'm looking at this here, and it looks like this is the return 0, and we don't want that, basically. We'll just delete this, and the code to pop the stack was actually 64. It should be matched, right? It should be matched because up here, you can see that we allocated 64, so when we pop the stack, we'll need to deallocate exactly the same amount of space. And then on top of that, the other thing we did was to refresh the the return address off the stack, because this is going to be a non-leaf function when we're done with it. So it returns it sets the return address, pops the stack, and returns. So all right, so basically, oh, and if you remember, we labeled this particular part as done, because the base case uses the same exit point as the recursive case. So that leaves this as the main meat of the code here. So we're going to compare W0 to 1, and we're going to branch less than or equal to return 1. All right, so that'll jump off to our base case. That means that this fall through slot is our recursive case. Subtract W0, W0 minus 1. So basically, if you're looking at this code on entry to the function, we have not modified the value of n. Therefore, when you arrive at this particular line, W0 still contains n. So this is setting the argument n minus 1 into the first argument register. We'll branch and link to fact, and then after that we will refresh the value of n. Remember, because argument registers are not saved registers, we will multiply W0, W0, and W1, and then that is our exit point for the recursive case. And again, remember, the register for returning stuff is in W0, so if we fire off this instruction, we don't need to have additional instructions to shift the result into any kind of register that the caller would expect. We need our base case now, so I noted here this was the end of fact, so I'll put it somewhere up here, basically. We call it RET1, all right? And we just move the value of 1 into W0, and then we will unconditionally branch to done. All right? Okay, so there you have it, a modified factorial code. Now what we're going to do is compile this thing using GCC. All right, so that command is GCC, display all warnings, do not optimize. We want the output to be main.out, and we want to compile from our .s file. Remember to make that change there. We're not working with C code at this point. Let's go ahead and compile this thing. No errors. All right, so if I had called fact of an argument 5, what should the value be? Maybe you want to quickly Google that. What answer do we get? 120. All right, cool. That makes sense to me, people. So that worked out. All right, so next videos we're going to cover recursive Fibonacci, as well as binary search and potentially a merge sort. Have a great day, everybody.